Good evening. I hope you can see me, hear my voice. Okay. I hope my presentation is visible.
Yes.
Okay, so I'm going to start. I'll wait for a couple of minutes so that if other students want to join. So I'll be discussing what's been covered in week 5, and then I will be doing questions related to Routh Hurwitz criteria and also the performance, how we decide the region on the left hand side based on the given performance specification. So some questions based on that. After week 4, we have seen about the controllers, type of controllers we have studied, proportional integral derivative controllers, and also the combination of all these controllers. And we have also seen how we can stabilize the system by using the controllers. So even for the unstable plant transfer function, we have seen how we can use any of the controller block and we can stabilize the system. So how do we check? How do we check whether the closed loop system is stable or not? First, we find the closed loop transfer function, right? So closed loop transfer function is this one. Okay. So this is the closed loop transfer function. So in this particular question, 1 by s square plus 1. Okay, so this is marginally stable open loop transfer function. So if you see, this is g of s, not g of s, we'll call it p of s, and this is c of s, right? So in a particular transfer function, in a transfer function where it is not stable, where the roots are lying on the left hand side of s plane, we'll be using cs such that if we find closed loop transfer function, okay, so it will have numerator and denominator. So we'll try to put all the roots of ds in the right hand side. Okay. So for the first secondary degree equation depends on polynomial. Okay, for second order we have seen, we can easily find out. Okay, so this type s square plus like as plus bs plus c type we can find out. Okay, we can easily find out the roots and we can find out when it is stable. But for a degree greater than 2, so you cannot, it's very hard, it's very difficult to find out the values of parameters. So that's why we are using Routh's criteria. Okay, so we have also studied about the Hurwitz polynomial. So it's a Hurwitz polynomial is said a polynomial is said to be Hurwitz when its roots have negative real parts, right? So negative real parts means if you say our polynomial is in terms of s, suppose this is our polynomial, so our roots should lie here. Okay, that's what it says on the left hand side. Okay, so we want to prove a polynomial or denominator, like I have written here. A closed loop transfer function is ns by ds. Okay, ns is numerator part and ds is denominator part. So what we want is, we want to prove ds is Hurwitz polynomial. If we prove ds to be Hurwitz polynomial, then we'll say the closed loop transfer function is stable, because when we say when we say this polynomial ds is Hurwitz, that means its roots have negative real parts, right? So negative real parts means it's lying on the left hand side of complex plane. Okay, so this is what we have studied. So how to find out? So what we do is we make Routh's array, right? So for polynomials of order 3 and more, a necessary condition, first is necessary condition. So for what is the necessary condition is, all the coefficient must be non-zero and of the same sign, right? So also we have seen in examples also all the coefficients should be should be non-zero and they were having positive signs, okay? Positive or negative signs. So its sign should be same. So how to build the array? Okay, so that's how to build the Routh's array. So we try to fill in first and second row. Okay, so whatever the coefficients of that polynomial is, we try to fill in first and second row, and based on that, we'll be finding this column, right? We'll see. We'll do the examples also. We'll do questions on that. How to find out B1, C1. Okay, that it's already shown here. Okay, once again, we'll practice that also. So that is given in the lectures. Okay, so what is the sufficient condition? Sufficient condition is the number of sign changes in the first column. So this is first column. Okay, so the column that I'm shading here, so this is the first column. Okay, the number of sign changes in the first column of the Routh's array should be 0. So for a polynomial, okay, for a polynomial, for its roots to lie on the left hand side, if its sign changes in the first column should be 0. Okay, if there is any number of sign change, then we will say those number of roots are lying in the right hand side. Okay, so it's Routh's array is equal to the number of roots of DS in RHP. Okay, that also we have seen. So we have seen examples also. Okay, these two example you can closely watch. So Routh's stability criteria means we have to follow necessary condition and sufficient condition. Okay, so point A is what? All coefficient of DS are non-zero and of the same sign. Okay, this is the necessary condition, right? Once we satisfy the necessary condition, we go on and take the Routh array and check for the condition B. Okay, then condition B, what should be there? The first column of the Routh's array constructed using the coefficient of DS has all entries being non-zero and of the same sign. Okay, so this is the sufficient condition. If all the all the coefficients, I think first column coefficient, yeah, in the first column, if there is all the these coefficients are non-zero, then we'll say the system is stable. Okay, so we have also a condition where some of the elements are equal to 0, so we'll follow this. Okay, so we try to replace the 0 with some small zeta here and go on with our calculation, and after that we'll check whether we have a sign change or not. So how do we check sign change? So we'll check sign change here. Okay, so above 0 and below 0, if there is a sign change, then we'll say there is a root of this polynomial which is lying in the right hand side. Otherwise, what do we say? There exists a pair of roots on imaginary axis. Okay, so it is like marginally stable system. Okay, it's not stable system. Okay, so it's already discussed in this particular question. Okay, so other case they have discussed is when your entire row becomes 0. Okay, so what they do, they try to find the auxiliary polynomial here. So how to find the auxiliary polynomial? Just take this row above that one, above 0 1. Okay, and you build this polynomial PAS equal to 6S4. So this one. Okay, you try to build this polynomial, and if you differentiate it, you get the coefficient. Then you replace this 0 0 with this one. Since only we have s cube term, so that's why we are putting here 24. So if you see this one and this one. Okay, so again we'll be using this. So what is the significance of this auxiliary polynomial when we'll have 0 0? So we know we'll have a radially opposite roots. Okay, so this is how radially opposite roots are. So if you have root here, you'll have root here. These are okay, radially opposite roots. Okay, again same thing, we try to do it. So it's clearly it's discussed in this particular example. Okay, so once we know this, how to once we know whether the particular polynomial has it where the roots lie, so we can find out our closed loop transfer function. Okay, so we'll try to find out the characteristic equation roots, right? So this will be helpful. So the criteria that we have studied, we'll be using in our transfer function to find out the roots of the denominator so that we can find out whether roots are lying on which side. Okay. So earlier we were facing some problems, right? So here with the application of this Routh's array, we'll be able to find out. Okay, so this equation like we have also studied in 4 tutorial 4 where we were using this formula, right? So to find out whether what value of Kp and Ki, okay, we should choose such that the system is stable. So we were using this particular formula plus minus b square. Okay, Kp plus 1 b square minus 4 1 into Ki by 2a. Okay, based on this, again we are building cases, case one, case two, and this and that, and then we are finding out what is the value of Kp and Ki so that the system is stable. So here it's very simple, like it's a cube. You build the Routh array and you just find out the first column, right? And it becomes very simple rather than doing this. So this is for the second order. So I have wrongly written for this particular equation. Okay, but we'll see how easy it is to find out where the roots are. Okay. 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 So again, one more in the last lectures we have studied what we have studied how to convert performance specification into desired region of closed loop poles. Okay. So so we know a particular system is stable. That means its roots are lying or its poles are lying on the left hand side. Then how to like tune that system so that our performance specification is met, right? So that we have studied here. So you see here. So we know through this particular example, what is given. Okay. So settling time is given. So this is again one desired performance specification and overshoot is given. Based on this two specification, so we have found out the region where we can put our poles, right? So we are narrowing this region. Okay, so that also we have seen. So so this is not exactly the procedure. We will also study other techniques also where it becomes very simple to actually put your poles there and get the desired specification. So this is just how to use the Routh criteria and place the poles to find to get the performance specification. Okay, there are also some questions are there. We'll do that. And again, it's how to get the steady state error. So you use this formula. Okay, ES equal to RS by 1 plus GS into HS. Okay, you can get this if you try to solve this. Okay, you can write equation from here. You will get this ES equal to RS by 1 plus GS into HS. Okay, and what we are interested is in this ESS equal to. So we are trying to find out what is the steady state error. Okay, so limit t tend to infinity u of t, that is equal to limit s tends to 0 s into rs 1 plus gs into hs. So rs is our input. Okay, and also we have studied what is type of the system, type 0, type 1, type 2. So for gs hs, okay, we try to find out if we don't have any pole, we say uh, any pole at origin. Okay, we don't have any pole at origin. So basically this equation, if you try to see this, okay, so see the denominator part. Okay, so if we have pole at origin, we'll say it's a type 1 system. If we have two poles at origin, we'll say type 2 system. If we don't have any pole, we'll say it is a type 0 system. So this is for GSHS. Okay, so this is open loop transfer function. Okay, so up to now we have studied. So we have not studied further. Okay, so any doubt up to here in steady state error or this one, Routh Hurwitz criteria, Routh's criteria. It's very simple. So I'll be doing questions. Okay. So this is very simple question. First one. If all the roots of the polynomial lie in the left half of the complex plane, then that polynomial is called. So you studied, right? Hurwitz. Okay. So we'll be using this concept to find the stability, right? What does Hurwitz? How do we say a particular polynomial is Hurwitz or not? Okay. So let's take the example of closed loop transfer function. Okay. So already I have discussed this ns by ds. So what we want is we want all the roots to lie in left hand side of this plane. Okay. That means what? Poles have negative real part, right? So we'll say this ds is Hurwitz polynomial, right? Very simple. So this is this plane. Okay. So if roots are lying in this, so with respect to control system, we are studying this, right? So this is mathematics concept. So if roots are lying here, okay, then we'll say roots of ds are lying in this. Then we say ds is Hurwitz polynomial. I think this was very simple. Any doubt in this? So this was the definition of Hurwitz. Okay.
Okay.
We'll go to the second question. Okay, the polynomial is given, okay, where k is real valued parameter, has all its roots in left half complex plane for all. Okay, so that's what I was saying. Okay, so this is the polynomial that is given. Okay, where k is real, right? So already the question specifies that its roots are lying in the left half complex plane. Okay, so it's very simple. So first is necessary condition, right? We know k minus 1 should be greater than 0 and k minus 2 should be greater than 0 and should be of the same sign. Okay, because if you see this coefficient 1, okay, so it is positive, so k minus 1 has to be greater than 0 and k minus 2 has to be greater than 2. K minus 2 has to be greater than 2, 0, sorry. Okay, so you know k is greater than 1 and from here you get k is greater than 2. Okay, simple, necessary condition we are applying here. And also from the lecture you have seen, for this second order system, necessary and sufficient condition is same, right? So you can also prove, you can write Routh's array for this to check for the sufficient condition. Okay, let's check it. Okay, this is 1, this k minus 1, this is k minus 2. Okay, so how do we get the coefficient here? K minus 1 into k minus 2 minus 1 into 0. So what we are doing is this. Okay, this is 0. Okay, and divided by k minus 1. So we'll get k minus 2. Same. Okay, so we'll see this column. Okay, so we know, so what we know. There shouldn't be any sign change, right? Okay, okay. So one is positive. So k minus 1 has to be positive, right? Because we know already it's given in the question. all its roots are lying in the left half complex plane. Okay. So k minus 1 is should be greater than 0. Again, if k minus 1 is greater than 0, if we go from k minus 1 to k minus 2, okay, we are going from here to here. Again, there shouldn't be any sign change. Okay, so this. So you know that this condition was same as necessary condition. Okay, k should be greater than 0, k should be greater than 2. But you know, we'll take this. Okay, intersection of these two conditions. Final condition is k should be greater than 0. Okay, if we have k greater than 0, then poles lie in left half plane. Okay, so any doubt in this question? It was very simple. Okay, so it's very simple in the sense we don't need to construct Routh's array. Okay, so in this case, necessary condition is sufficient condition because the order is second, right? So the solution, the final answer is k should be greater than 2. So any doubt in this case? Very simple question. Okay, so how this question becomes simple? Okay, so you can check by this Routh's array also. Okay. Okay, any doubt in this case? Okay, I'll go to the next question. Okay, the polynomial has, so okay, so this is third order. Okay, 8 square plus 22s plus 20 equal to 0. Okay, so we'll see how this Routh's array becomes handy here. Okay, so here it's 3. Okay, so let's first check the necessary condition. Okay, so what is necessary condition for this? Okay, so all the coefficients are present, right? You see, all the coefficients are present. So I'll just mark those coefficient here. The coefficient is 1, coefficient is 8, 22, and 20. And all the coefficients are, first condition of all the coefficients are non-zero and all the coefficients have same sign, right? So all the coefficients have positive sign. Okay, so necessary condition is met. Okay, let's go to sufficient condition. Let's check for this. Okay, so what we have to do, we have to construct outside it. Okay, so let's build that. Q square is 1, 0. Okay, so coefficient of SQ is 1, 8, 22, which is 20. Okay, I hope everything is correct. 1, 8, 22, 20. Exactly. So how to find the, this is, I will call B1. Let me call this C1. Okay, so what is B1? B1 is 8 into 22. Okay, 1 into 20 minus 1 into 20 divided by 8. Okay, how much you're getting? Getting 19.5. Okay, similarly, how to get C1? C1 is B1, which is 19.5 into 20. Okay, minus 8, it's 8 into 0. okay, divided by 19.5. So you'll end up with 20. Okay. Okay. So you see this first column. Okay. Okay. So the elements of this first column is positive, non-zero and positive, right? And there is no sign change. So what can you say about this? What can you say about roots of this polynomial? Okay, the first option, if you see all its three roots in the left half complex plane. Okay, so all its three roots lie in the left half complex plane because there is no sign change. Okay, so this option is true. Okay, so any doubt? So degree of this polynomial was 3. Okay, so first we check necessary condition. So what is necessary condition? So all the coefficients should be non-zero and of the same sign. So here all the coefficients are present and all the coefficients have positive sign. Okay, then to check for the sufficient condition, we constructed Routh's array. Okay, so this is how we constructed Routh's array, and after constructing, we found out we are seeing this first column. Okay, so what we observed that there is no sign change here. Okay, 1, 8, 19.5 and 20. So all the elements of this column is positive. Okay, so we came to the conclusion that the roots of this polynomial are lying in the left half side, left half side of the complex plane. Okay, any doubt in this question? So that's why it's all its three roots are lying in the left hand side of complex plane. Okay, I think this is a very simple question. Okay, this question 4. So we're given polynomial. So again, we have to find out where the roots of these polynomials are lying. Okay, so 5s square plus 2s plus 12. Okay, you see the sufficient condition. So all the coefficients are non-zero and they are of same sign. Okay, so just we'll construct Routh's array. Okay, just directly go to the sufficient condition. So constructing Routh's array is cube is square, so 1 is 0. Okay, so 1 5, this is 2 12. Okay, 1 5 2 12. Okay, so again let me call this b1 c1. Okay, so what is b1? b1 is 5 into 2 minus 1 into 12 by 5. Okay, so 10 minus 12 is 2 by 5. Okay, so this is minus 2 by 5. Okay, let's find out what is c1. c1 is minus 2 by 5 into 12. Okay, minus 5 into 0 divided by minus 2 by 5. Okay, so what you will get? You'll get 12, right? Simple. Directly you can see, you can write 12 here. Okay, so what we'll see in this first column. Okay,
There is a sign change.
so what you see is this. Okay, correct. Okay, so total 2 sign change. Okay, this is first sign change. Okay, this is second sign change. So we have total of total sign change equal to 2. So what can we say about the roots? So, okay, so it has total 3 roots, right? So it has degree 3, right? So it has 3 roots. So what we can say, two roots of, let me call this polynomial p of s. Okay, so two roots of ps lying right hand side of complex plane. Okay, okay, suppose it's a denominator of a closed loop transfer function. Okay, directly we can say the closed loop transfer function is unstable. Okay, so any doubt in this? Very simple. So there were two sign changes, so that's where we said two roots of this ps lie in the right hand side. Okay, simple, very simple. So let's see the options. All two, three. First option is anyway incorrect. Two roots lie in the left hand complex plane and one root. This is also incorrect, right? So third one is one root lie in the left half complex plane and two roots in the right half complex plane. Okay, so this is correct. Okay, so one root lie in the left half complex plane and two roots in the right half complex plane. Okay, so any doubt in this question? Very simple question again. You have to construct the Routh array and just check the sign for the first column. Okay. Fifth question again same. The polynomial has now the degree is 4. Okay. Let's check for this also. Okay. Just check the necessary condition. Okay. See all the coefficients are present, right? All the coefficients are present. That means they are non-zero and also sign is they're all positive. Okay. The necessary condition is met. So let's check for the sufficient conditions. So we have to construct Routh array. Okay. Okay, this one, 3, 6, 12, 8. Okay, so let me call this P1, C1, D1. Okay, this is B1 and B2. Okay, let's find out this is C2. Okay, let's first find out what is P1. P1 is what? 3 into 6 minus 1 into 12. Okay, by 3. So this is 6 into 3 is what? 18 minus 12. Okay, so 18 minus 12 is what? 6. 6 divided by 3 is 2. Okay, just see my calculation. If I am making mistake, please interrupt me. Okay, so P1, so B1 was 2. Okay, 3 into 6 is 18. 18 minus 12 by 3. Okay, coefficients are 1, 3, 6, 12, 1, 3, 6, 12, 8. Correct. So let's find out what is B2. So B2, okay, B2 should be 3 into 8 minus 1 into 0 by again 3. Okay, so this is 8. Okay, so let's find out what is C1. C1 is 2 into 12 minus 3 into 8 by 12. Okay, we are going like this. 2 into 12 minus 3 into 8 by 2. Okay, so this is 24 minus 3 into 8, 3 into 8 is again 24 by 2. So this is equal to 0. Okay, so how to find C2? C2 is not there. Okay, so let's not try this. So again, what we have encountered here, you see in this particular row, 0, right? So what we used to do, we'll replace this with very small value. Let me call this epsilon. Okay, okay. Then do the calculation with this. So it's very, this is what is small positive value. Okay, very small positive value. So getting a 0 has some consequences, right? We'll have poles on the imaginary axis that we have seen. So let's carry on and find out D1. Okay, what is D1? D1 is ln into 8 minus 2 into 0 by ln. So D1 is 8, right? So this is 8. Okay, so just see this column. Sorry, yeah, we change the color. Okay, so we have encountered a 0, but there is no sign change, right? So if you see these elements, so what are critical element? This one and this one. Okay, so from 2 to epsilon and from epsilon to 8, there is no sign change. Okay, so there is no sign change. That means there is no roots of this polynomials that are lying on the right hand side. Okay, but since we got this 0 in this S1 row, so what we can say, there are roots lying on the imaginary axis. Okay, so what we'll say, so roots are lying on the imaginary axis. Okay, so also imaginary roots are conjugate pair, right? So if we have one pole here, we'll have another pole here. Okay, so how many poles are lying on the imaginary axis? Two roots. Okay, so two roots lie on imaginary axis. Again, since the degree of this polynomial is 4, so what we can say, two roots are lying on the imaginary axis, the rest of other two roots lie on the left hand side. Okay, again, two roots lie in left half of complex plane. Okay, okay, it can be anywhere, here, here, it can be here, here, anywhere. Okay, because of the 0, we are getting roots here on the imaginary axis. Okay, so this was the consequence of the 0. Okay, okay, so let's see the option. So first option is all its 4 roots in the left half complex plane. So this is incorrect, right? 2 roots on the imaginary axis, correct? Third option is 2 roots in the right half complex plane. This is incorrect. This is incorrect. Last option. So any doubt in this case? Okay.
Yeah, how to find
So
that
we have
exactly
constructed
two
the
roots
Routh
on
array,
the
and what
imaginary
we
axis?
found out. Okay. Because how to, okay, because the imagine the roots lying on the somewhere here. Okay, so conjugate root, like some root we call a. Okay, so you'll be having roots like this plus jb, right? A plus minus jb, so two roots are s1 equal to a plus jb and a minus jb. Okay, so they always come in pair, right? That's what we know. they always come in pair, right? So if roots are lying on the imaginary axis, that means only a term is equal to 0. Okay.
Okay.
So a term is equal to 0. That means you'll have S1 equal to JB and S2S minus JB. So that's why out of 4 we know 2 roots are lying on the imaginary axis. Okay. So about this 2 roots lying on the left half complex plane, we can roots can be here also. So these 2
That means
roots
if
can be
one,
here also. Okay. If they are here, that means a
one,
conjugate pair will be lying here. Yeah. Yes. Any doubt?
suppose there are 2 0 in the Roth's array.
Can you repeat the question? I didn't hear you. Okay.
So what I understand, if I have one 0 in the roots array, and I assume that I understand that there are roots
Okay.
on the imaginary axis. Am I correct?
Correct. Correct. Yeah. Yeah.
Then you say that S is equal to A plus JB. That means 1 0, you have to take one S equal to A plus or minus JB.
Yeah.
Okay.
Yeah. For this
Okay.
case, you just make it 0. So
Okay.
this was the case. So when we have this once again, if we encounter this condition, so that means this is roots are like this plus minus JB somewhere.
Okay.
Okay.
Okay. I
So you
understand.
can find the roots also. So how to find that root? Go to this. We can make the auxiliary polynomial. Okay. So it's like 2s square plus 8 equal to 0. Okay. So this is auxiliary polynomial as. Okay. So if you solve this, s square plus 4 equal to 0. Okay. S is what? Plus minus j2. Okay. So we also know the location of its roots that are lying on the imaginary axis. So S1 is plus J2 and S2 will be minus J2. Okay, that also we'll see. So if you want to be more specific, this will be plus 2J and this will be minus 2J. Okay. Okay. I hope there is no doubt here. Okay.
Okay.
Go to this question, sixth question. Okay. Thank you. Consider a second order plant governed by this equation. It is desired to design a unity negative feedback. Okay, so unity means HS is equal to 1. Closed loop control system with this plant. Okay, which one of the following statement is true? So you have to find out which controller can stabilize this transfer function, this particular plant. Okay, let's first find out the transfer function for the plant. So its equation is given. Okay, it's apply the Laplace transform. So y of s by u of s. This is p of s. Okay, so which is 1 by s square plus 4. Okay, so ps is given, so it's like this. So you have to find out cs. Okay, which can stabilize the closed loop transfer function like this. So this is negative, it's given already, and HS is equal to 1. Okay, this is y of s. Okay, so what we call this as g of s, right? So let me also write down h of s. So this is h of s. Okay, so what we want is closed loop transfer function. The closed loop transfer function will be y of s by r of s. Okay, so which will be equal to, already we have studied, gs 1 plus gs hs. Okay, because hs is okay, hs is equal to 1. Okay, because it's already given in the question. So what we have to find out, it is desired to design a unity negative feedback closed loop control system with this plan. Which one of the following? Okay, so you have to find out which of the controller can stabilize this closed loop system. Okay, so CS can be anything. So let me first find out G of S. Okay, so you know P of S. So for the first, let us first see the first option. Okay, the closed loop system can be stabilized with a proportional controller. Okay, let's try first with the proportional controller. So you know the transfer function of proportional controller is just Kp. Okay, then what is G of S? G of S is C of S into P of S. Okay, is equal to Kp into 1 by s square plus 4. Okay, so let me just write Kp by s square plus 4. Okay, and what is the closed loop transfer function? Gs, which is Kp s square plus 4 divided by 1 plus Kp s square plus 4. Okay, so what we'll get, Kp by s square plus 4 plus Kp. Okay, so this is closed loop transfer function. Okay, so you'll see this. Okay, just see the denominator part. Okay, that's what we are talking about. So let me call this ds as ds s square plus Kp plus 4. Okay, so what can be the values of Kp so that this closed loop transfer function is stable? Okay, so we cannot Kp from negative value to positive value. Okay, but you see here, see this Kp plus 4. Okay, so what was the condition? Routh stability criteria. Okay, necessary condition is not met. So here the coefficient of S is absent. Okay, it's 0. Okay, so just recall first necessary condition. All the coefficients should be non-zero. So if you see here, the coefficient of S is 0. Okay, so even necessary condition is not met here. Directly we can say, okay, so what can we say? Directly we can say CLTF is unstable. So we are not commenting anything about marginal stability on. We are just saying it's unstable, right? So any doubt in this case? So coefficient of S is 0. So that's why we said even the necessary condition is not met. That's why the closed loop transfer function is unstable. So that's why any value of Kp you put, it cannot stabilize this particular plant. Okay, so this statement is wrong. A closed loop system can be stabilized with proportional controller. No, it cannot be stabilized. Okay, because the coefficient of S is 0. Okay, so let's check with the second option. The closed loop system can be stabilized with an integral controller. Okay, case 2. So what is the transfer function of integral controller? Ki by s. Okay, so g of s is c of s into p of s. Will be ki by s into 1 by s square plus 4. Okay, so let's find out the closed loop transfer function. Hs is equal to 0. Okay, so ki s into s square plus 4, 1 plus ki into s square plus 4. Okay, so what you'll get, ki square plus 4 plus k. Okay, so this will be s cube plus 4s plus ki. So again, if you see the ds here, s cube plus, so I'm writing like this. Okay, so if you see this, the coefficient of s square is equal to 0. Okay, even the necessary condition is not met here. Okay, so what can we say about this polynomial or this closed loop system? It is unstable. Okay, so whatever the value of ki you put from minus infinity to infinity, it will not be, it is insufficient to stabilize this closed loop system, right? Because you'll never have the coefficient of s square to be positive or anything non-zero number. Okay, so that's why what we can say, CLTF is unstable for any value of ki. Okay, so integral controller cannot work here. Okay, let's check for another controller. So third option we have proportional integral controller. Okay, proportional. Okay, so C of S is what? Kp plus Ki by S. Okay, so this is the transfer function for the controller. So what we can write, S into Kp plus Ki by S. Okay, so let's first find out what is G of S, which is C of S into P of S. So P of S is plant transfer function. Okay, so this is into 1 by s square plus 4. I think correct, s square plus 4. Okay, so this is G of S. So closed loop transfer function is G of S 1 plus G of S. Okay, S into Kp plus Ki. This is S into s square plus 4. So this is 1 plus same term, S into Kp plus Ki, S into s square plus 4. Okay, so in the numerator you'll get S into Kp plus Ki, okay, divided by S into s square plus 4 plus S into Kp plus Ki. Okay, so this is s cube plus 4s plus S into Kp. So you can just club this S term, 4 plus Kp into S plus Ki. Okay, so what is D of S? Okay, again s squared coefficient is not there. So I can write 0 into s square plus 4 plus kp into s plus ki. Okay, again the same thing. Coefficients are, this coefficient is 0. Okay, so necessary condition is not met. So what we can say about this? Proportional integral controller cannot stabilize. Okay, cannot stabilize this system, closed loop system. Okay, so this is also wrong. Okay, let's check for the last one, because anyway this has to be correct one. Okay, proportional derivative controller. So fourth one is proportional derivative controller. Okay, so C of S is equal to proportional Kp derivative S into Kd. Okay, so G of S is equal to C of S into P of S. Okay, so Kp plus S into Kd S square plus 4. Okay, so closed loop transfer function is G of S divided by 1 plus G of S. So G of S is Kp plus S into Kd. Okay, square plus 4, 1 plus Kp plus S into Kd square plus 4. So what you'll get? Square plus 4 plus Kp plus S into Kd. Okay, so this is closed loop transfer function, and D of S is, so let's arrange it properly, S square plus S into Kd plus 4 plus Kp. Okay, now you see, so degree of this polynomial ds is 2. Okay, so you know for this necessary and sufficient condition are same. So for this Kd, because here the coefficient of s square is equal to 1, so the coefficient of s and s0 should also be positive. Okay, and greater than, and they should be positive and non-zero, that means greater than 0, right? So this has to be there. So Kp is greater than minus 4. Okay, so if we have Kd greater than 0 and Kp greater than minus 4, if we satisfy this condition, then proportional derivative controller can stabilize the closed loop plant. Okay, or you can say closed loop system. Okay, plant system. Okay, any doubt in this case? So we are in, just focus on this equation. Okay, so s square plus s into kd plus 4 plus kp. So all the coefficients should be non-zero and they should be greater than 0, right? Because coefficient of s square is greater than or it is equal to 1, right? Positive. So all the coefficients should be positive. So that's why if we place that condition, kd is greater than 0 and kp is greater than minus 4. Okay, if we satisfy this condition on kp and kd, we'll be able to stabilize this closed loop system. Okay, so this statement is correct. Okay, so in the previous 3 cases, one of the coefficient was missing. Okay, so necessary condition itself was not, we are not able to satisfy the necessary condition. So that's why we are saying the closed loop system is unstable, or that particular controller is not able to stabilize the closed loop system. Okay, so any doubt in this particular question? Very interesting question. Okay, so that's how actually we stabilize the system. We are given with a plant and we choose C of S such that the closed loop transfer function is stable. Okay, so any doubt? Okay, we'll go to the seventh question. So it is desired that the closed loop system should have a settling time below 1s. This requires that the real part of the closed loop poles be less than. Okay, we have to find out what should be the real part. So when we are saying about this settling time, that means we are having, or the system is approximated to second order system, right? Because this parameters are only defined for the second order system, right? So for the second order system, what was the settling time for 2% error 4 by zeta omega n, right? So this was the settling time, right? Or I'll write second order system. Okay. And it is desired that the closed loop system should have a settling time below 1 second. What is desired is this. Okay. And we have to find real part, right? So real part of the second order system. So we have seen which was equal to minus zeta into omega n. Okay. Plus minus. So you have seen this one also. Root of 1 minus. So this is for 100 times I'm writing. Okay. But this is the real part, right? So I'll say this is the real part. Okay. So this is S. S is pole. Okay. So real part is minus zeta into omega n. So let's find out zeta into omega n. So, okay, let's solve the inequality here, which is this. Okay. So if we put negative, then the sign will change. Okay. So this is real part, right? So your real part, so right, in terms of real part should be less than minus 4. Okay. So this requires that the real part of closed loop pole should be less than minus 4. Okay. So any doubt in this case? So we are given with TS. Okay. So let me also draw the S-plane diagram. This is imaginary, this is real. Okay. So real part should be less than this. That means this area. Or let's say this area. Okay. So it will not say this. So if you have poles here in this area, shaded area, you will have settling time less than 1 second. Okay. So this is minus 4. Okay. So any doubt in this question? So answer for this question is the poles, the real part of the pole should be less than minus 4. Okay, this area. Okay. Next question. It is desired that the closed loop system should have maximum peak overshoot below 15%. So peak overshoot is this. Okay. In terms of percent, it should be less than 15%. Okay. So what we have to find, this requires that the damping ratio of the system be at least. So we have to find out minimum damping ratio of minimum zeta. Okay. So this you have to find out. So by solving this, okay. So just try to do calculations. Okay. So this is eta pi. Okay. So this should be less than 0.15. So taking natural log on both the sides, what you'll get. What is natural log of 0.15?
Minus 1.89.
Okay, okay, do the calculation. Minus 0.89, right? Okay, so let me solve this.
So 1.89.
Okay, this is 1.89. Okay, if we just remove the minus sign, we'll get change the equality to this 1.89 squaring on both the sides. So we'll get this 1 minus zeta square. Okay, just taking 1.89 pi square into zeta square is 1.89 square. Okay, so let me take this zeta square common here, pi square plus 1.89 square square. Okay, so we take the, this is square, if you take the root, you will get 1.89 divided by pi square plus 1.89. So if you solve this, what you're getting? So just, okay, just solve this. I think some 0.516 you're getting, you'll get something. Yeah, you're getting something.
0.515.
Yeah, so we can approximate it to, okay, let me say you're getting this. Okay, so your damping ratio should be greater than this value. Okay, then you'll get the overshoot, which will be less than 15%. Okay, so this is the answer. Okay, so if you have zeta which is greater than 0.516 or 517, then you'll have your P maximum peak overshoot, which will be less than 15%. Okay, that's what we have seen, right, in the theory also. So if you see the response, okay, let me make the unit step response. Okay, so this is the response, right? What will happen if I increase the zeta? So here this peak overshoot also reduces, right? So if I further increase zeta, I will get this response. Okay, so you see here if you see peak overshoot will decrease. So this was initial peak overshoot, then this is second is peak overshoot, then third if I further increase the zeta, then you will get this. Okay, so you're getting it, right? So you can see if I keep on increasing zeta, the maximum peak overshoot will also decrease. Okay, Okay. So any doubt in this question?
I didn't understand the last point, what you said.
Okay. So in the last part, if you see the response of the closed loop system, okay. So if for a unit step, okay, so for a unit step, let me write. So for, let's assume for under time response, right? Because we have zeta which is less than 1, so you'll get under time response. Okay, so you'll get response something like this. Okay, this you know. For a particular zeta, I'm saying, so it has some zeta 1. Okay, so what I do now, and this is the MP, peak overshoot, right? So what I do now, I increase the zeta. Okay, so I'll get like this response. This is the response. So what you will get, this will also reduce. Okay, so for zeta 2, you see this is peak overshoot MP, and other one is this. Okay, so the peak overshoot reduces, right? So zeta 2 is greater than zeta 1, and MP, this is 2. Let me write 2, or because I'm using same color, 2. Okay, it's less than MP1. That's what I was saying. Okay, just
Got it.
I was comparing to output response for a unit step input. Okay, this you will see. Okay, and also you can see
Sure.
in the complex plane also how, because you can get the beta, right? Here also you can see you will narrow the region here, something like this. Okay, you can get the exact value also. I think this was also discussed in the lecture also. That's why I am not discussing this. Okay. Okay. So any doubt in this question? Okay, we'll go to the next question then. In problem 6, the constraint on the controller parameter of a proportional derivative controller that would always stabilize the closed loop systems are. So I think that we solved in problem number 6. Let me go to problem number 6. So this is problem number 6, right? So let me just copy this. So this is the closed loop transfer function, okay, that we are getting if we use proportional derivative controller. Okay, so it just already we have solved this. Okay, so denominator polynomial, if you see, s square plus skd plus 4 plus kp. Okay, already we have solved. That's what it is asking. What is the value of the constraint it is asking? You know, kd has to be greater than 0, and 4 plus kp has to be greater than 0. It should be non-zero, right? So kp has to be greater than minus 4. So kd greater than 0, kp is should be greater than minus 4. These are the constraints, okay, to stabilize the system. So which option is correct? kp is greater than minus 4 and kd first option. Okay, kp should be greater than minus 4 and kd should be greater than 0. I think already we have discussed this question. Okay, any doubt in this question? Okay, we'll go to the next question then. Consider second order plant governed by equation. It is desired to design a unity negative feedback. Okay, unity negative means HS is equal to 1 feedback control system with this plant using a proportional controller. Okay, so we will be using CS, which will be KP. The closed loop system would be stable for. So we have to find out for what value of KP the closed loop transfer function will be stable. Okay, So what is given? Let me first find out the plant transfer function. So minus 2 y u. Okay, so applying Laplace transform, you'll get s square y of s plus 3s y of s minus 2y of s equal to u of s. So this we are calling as p of s, plant transfer function. Okay, 1 divided by square plus 3s minus 2. Okay, so you can see this is unstable, right? If we just take the plant transfer function, this is unstable. Okay, because of this minus 2. Okay, if you use this criteria, Routh Hurwitz stability criteria, so one of the coefficient is negative. Okay, so but we have to stabilize this system. Okay, that's why we'll be using a controller. Okay, so we'll be using kp, and this is the transfer function, this is the plant. Okay, so this is controller and this is plant. Okay, hs is equal to 1. Okay, that is given in the question. So this is now what we are doing. So we are trying to stabilize this unstable plant, okay, using this controller kp. Let's check for what value of kp are we able to stabilize. First we are able to stabilize or not. Okay, so let's first find out g of s. You know what is g of s, right? So g of s is c of s into p of s. Okay, so this is c of s and this is p of s. Okay, just equal to kp by square plus 3s minus 2. This is g of s, and closed loop transfer function is g of s 1 plus g of s, right? hs, right, h of s is equal to 1. That's why I'm not use that. Okay, so kp 1 plus kp square plus 3s minus 2. Okay, so what we'll get, kp by s square plus 3s plus kp minus 2. Okay, so this is closed loop transfer function, and if you see the denominator polynomial, you'll get s square plus 3s plus kp minus 2. And what we know for this, okay, all the coefficients should be non-zero and positive for this. Okay, so kp minus 2 should be greater than 0 and kp should be greater than 2. Okay, if kp is greater than 2, then you know this term will be always positive, and if this term is always positive, then we ensure that the roots of this polynomial will always have a negative real part, right? That we ensure. Okay, that means our system is closed loop transfer function, or our system is stable. Okay, if kp is greater than 2, then closed loop transfer function is stable. Okay, so this is the condition. Okay, if kp is greater than 2. Okay, so if we are able to, if we keep the proportional gain greater than 2, then we'll be able to stabilize this system. Okay, so any doubt in this question? Very simple. So we are given with unstable plant transfer function, and we have to stabilize by using controller. And what controller? kp controller. Okay, so what we did, we found out the closed loop transfer function gs divided by 1 plus gs, and if you see the denominator polynomial, which is T of S, and just apply the necessary condition. So all the coefficients should be non-zero and of the same sign. Okay, and in this case it should be positive. So Kp minus 2 should be greater than 0, and Kp should be greater than 2. If we ensure this, we'll have closed loop stable system. Okay, so any doubt? So the correct answer is Kp should be greater than 2. Okay, go to the next question then. 11. In problem 10, the ratio of ES to RS is ES to RS. Okay, you can derive also. You have to find out this ratio. Okay. So, okay, should I derive it for you or not? Okay. Because it's already covered in the lecture, which is, I think this was equal to 1 plus GS into HS, I think. I think this 1 plus GS into HS. So let me try to derive it, okay. So GF is given. So this is the closed loop control system, right? Minus this is HS, and you have Y of S, and we have to find out this E of S by R of S. Okay, so E of S is what is equal to RS minus Y of S into H of S. Okay, and Y of S also, what is that? G of S into E of S. Okay, I'll write in the proper order. Okay, I think the equation first is E of S equal to RS, R of S minus Y of S into H of S is very clear. Okay, then I'm writing Y of S as E of S into G of S. Okay, so I'll just substitute this here. I hope I'll get the correct thing. Into G of S by H of S. Okay, so if I take this on the left hand side, you'll get G of S, H of S equal to R of S. Okay, so this is 1 plus G of S, H of S equal to R of S. Okay, so E of S equal to R of S by 1 plus G of S into H of S. Okay, if you just take this RS here, so you'll get this. Okay, so I just derived this, so it's, I think, not done in the lecture. Okay, so we'll get this finally. So final form was given in the lecture. Okay, so E of S by, so this is not G of S, this is R of S. Okay, E of S by R of S is 1 by 1 plus GS into HS. Okay, so what's given in the question, we have to find the ratio. Okay, so let's find the ratio. E of S to R of S, 1 by 1 plus H of S is, I think, 1 in every question that we have solved. So what is GS? So question number 10. In the previous question, what is GS? Okay, GS is this. Okay, so this is G of S. Okay, so directly I'll write here. So this is G of S. Okay, so solving this, you'll get S square plus 3S minus 2 in the numerator, and in the denominator finally you will get s square plus 3s minus 2 plus kp, or kp minus 2 you can write, kp minus 2. Okay, so this is the ratio you're getting. So let's check which option is correct. So numerator you have s square plus 3s minus 2. S square, this only option is this, s square plus 3s minus 2, and denominator s square plus 3s plus kp minus 2. Just see this. So any doubt in this question? Again, very simple. Okay, so any doubt in this, how we got this ratio, E of s by R of s equal to 1 by 1 plus 3s into hs? Simple, E of s is Rs minus this one, okay? Y of s into hs. So you can define any quantity here. So Rs is there, you can say this is what you can say, oh, x of s you can say. So x of s is, I have directly written, but you have to write h of s into y of s. I have directly written, okay? So that's what this is, this quantity x of s, okay? And again y of s, what is y of s? E of s into g of s. I think that that we have already seen in first week, okay? So just put y of s here in equation 1. So this is, let me call this equation 1. So putting equation 2 in 1, okay, substituting y of s, you'll get to this result. Okay, so any doubt? Again, very simple question. Okay, we'll go to the next question then. In problem 10, the steady state tracking error when the stable closed loop system is given a unit step reference. Okay, so this is the, so let's first find what is the closed loop transfer function. No, what is error first of all? So you have to find this steady state error. Which was equal to limit s tends to 0 s into rs 1 plus g of s into h of s. So that is there, okay? Steady state tracking error. Right, steady state okay. So you have to find out this because we applied final value theorem. So refer to the notes, okay? We'll directly use this and find out the steady state tracking error. Okay. So what we are given here? So RS is given, right? Which is unit step. Okay, 1 by S. Okay. So what is G of S from the question number 10? I think we also used in the previous question, right? This Kp by S square plus 3S minus 2. Kp by S square plus 3S minus 2. Okay. So let's use this and find out the steady state error. So limit S tends to 0, S into R of S is 1 by S, 1 plus G of S is Kp square plus 3S minus 2.
Sir, how the value of RFS is 1 by S?
You're saying this one?
No.
Okay, because it's already given in the question. You read the question. So steady state tracking error when the stable closed loop system is given a unit step reference. Okay. So R of S is unit step means what, you know, the transfer function if you apply. So unit step is this, right? One value. So if you, what is R of S? R of S will be 1 by S, right? So any doubt in this particular thing, why R of S is equal to 1 by S? Unit step,
No,
we are using this function, yeah, constantly. Okay, that's why directly I have written R of S equal to 1 by S. Unit means 1, okay, step response. So this is step input. So R of S is equal to 1 by S. So directly we'll use this. So okay, what you'll get, the numerator you'll get this, and in the denominator you'll get s square plus 3s plus kp minus 2. Okay, if you apply the limit, just put s equal to 0, you'll get minus 2 divided by kp minus 2. Okay, so this is steady state tracking error. Okay, 2 kp minus 2. Okay, or you can also write here 2. Just shift the negative sign to the denominator, then you can write 2 minus kp. 2 by 2 minus kp. Okay, if you see, option 2 is correct. So any doubt in this question? So to solve this question, you have to know this, right? How to get this expression? So previously I have derived this one. Okay, so you can use this here if you want the derivation. Okay, so I'll just use this. Okay, so you know this you got. Again, what is error? Error is this. So that's what we have used, rs by 1 plus g of s into h of s. Okay. So if you want to find out the final value, then this is what you do. S tending to 0, s into e of s. So that's why we are using this. S into r of s by 1 plus g of s into hs. Okay, directly I have used this. See? Okay, because we want to find out the final value of e of s, right? So that's how we find out. Okay. Final value theorem, if you just revise it, you will get it. Okay. Okay, so let's go to the next question, 13th question. So in problem 10, it is now desired that the real part of all closed loop poles to be less than -1, the range of proportional gain that would satisfy this requirement. Okay, in problem 10. So again, in problem 10, we are using, so let's first write what is g of s. Kp by adding s square plus 3s minus 2 was this one. And closed loop transfer function, what we found out, kp by s square plus 3s plus kp minus 2. Okay, so this was the closed loop transfer function. If I go to the question number 10, okay, so you see this closed loop transfer function. Okay, so this was the closed loop transfer function. Okay, okay, so it is now desired that the real part of closed loop pole should be less than -1. Okay, so what you want is this. So if we put kp, greater than 2, what we are ensuring is our roots are lying in this region. Okay, but what we want is now our root should lie here. So left of this line, okay, this line is -1. What you want is this, the range of proportional. Okay, so it is desired that the real part of all closed loop poles be less than -1. Okay, now what we want is this area. So we want now this area. Okay, earlier we found out Kp greater than, if we put Kp greater than 2, we'll have yellow portion, right? But what we desire now is this portion, red portion. Okay, so what we can do, so this blue one, so this is, okay, this is S plane. So what I will do is I will just shift this S plane. Okay, now I'll make the origin here. So this was the origin. Now I'll just shift this to -1. So how I'll do, I will use this. So this is S. So let me call this as Z. Okay, Z plane. Z plane. Z plane has 0 here at S equal to -1. Okay, so Z equal to S -1. Or okay, if I'm right, in second. Yeah. Okay. If you put S equal to -1, what you will get? Z equal to 0, right? You're getting it? I'm just shifting the axis, imaginary axis, to here. So what you will get? S equal to Z -1. Okay. So now I'll get polynomial in terms of Z. Okay. So this is ds, right? ds is s square plus 3s plus kp minus 2. Okay, just change in z variable, put s equal to z minus 1. Okay, I solve this. So this is z square plus 1, okay, minus 2s plus 3z minus 3 plus kp minus 2 equal to 0. Okay, just arranging this properly. So okay, this is not, this is z, I think is z. Okay, so this is plus z. Okay, so let kp, so if we have 1 3, 1 minus 3 and minus 2. Okay, so this is minus 4, I think, minus 5 plus 1 equal to 0. Just see the calculation. If I am making any mistake, please you can tell me. Okay, kp minus 4 equal to 0. Let me again check. So s square plus 3s plus kb minus 2 is the original equation. So we have shifted the axis. Okay, z equal to z plus 1. Okay, just put s equal to -1. So if you put in this equation, so let me shade this. If you put s equal to -1, what you'll get? Z equal to 0, right? That's what we have written here. Okay, we are shifting the axis. Okay, so s equal to z minus 1 then. Okay, just replace s with z minus 1. So okay, so z square plus 1 minus 2 of z plus 3 of z minus 3 plus kp minus 2. Okay, z square, then we'll have positive. So if you solve this, you'll have positive z minus 2z plus 3z is plus z, and you solve plus 1 minus, okay, this 4 terms. So what you'll get? Minus 5 plus 1 is this one. Okay, so what you want is now, if kp, so again this is again a if you see this polynomial z of s, okay, we can apply the same rules, right? Necessary and sufficient condition. Okay, what you want is all the coefficients should be non-zero, and in this case it should be greater than 0, right? So kp minus 4 has to be greater than 0. Okay, if kp is greater than 4, okay, so what we are ensuring here, if kp is greater than 4 in terms of z, in terms of this, so this is z plane. Okay, in terms of z plane, what we are ensuring is the roots are lying here. Okay, so we'll ensure this. But you know, this Z plane, okay, this is 0 for this. This is 0. Okay, but for S plane, what is this point? This is -1, right? So this is the Z plane. 0 is here. Okay, so we'll ensure that for S plane, all the roots will be lying, or the negative part of pole will be less than -1. Okay, if we keep Kp to be greater than 4. Okay, so option 3 is correct. Okay, we are just shifting the axis here. How we shift the axis? Putting Z equal to S plus 1. Okay, so at -1 point, I'm making that as origin. Okay, so I'm calling that as Z plane. So Z plane has origin at S equal to -1. Okay, so if I do the substitution, I will get this. So any doubt in this question? Okay, so this substitution is critical. Okay, we'll go to the next question then. The open loop transfer function corresponding to problem 10 is, okay, we have to find out the type of the open loop transfer function. Okay, you know, open loop transfer function is h of gs, gs into hs. Okay, open loop transfer function. Okay, and hs is equal to 1, and open loop transfer function of which question? Question 10. Okay, g of s, you know, is equal to kp by s square, okay, plus 3s plus kp, not kp, I think it was -2. Okay, I think this was the open loop transfer function. Yeah, you see this g of s equal to kp by s square plus 3s minus 2. Okay, so this is the Planck transfer function, and if you multiply by cs of, you'll get g of s. Okay, this is the open loop transfer function. So what can we say? Just find out. So this is d of s, right? And we can easily see, though it is unstable, but it does not have any pole at origin, right? Okay, so if we want to write, if we write this s, so 3s minus 2. Okay, so you see this 0, right? Nothing. It doesn't have any pole at origin. That's why I'm writing like this. Directly you can look and you can say, so this open loop transfer function does not have any pole at origin. That's why it is type 0 system. Okay, very simple, this one. Okay, suppose if, let's suppose closed loop system is like this, kp by s square plus 3s. Okay, so now what I can do is I can write like this, s, I can take s common, s plus 3, right? So what we say, we have a pole at origin. Okay, so what is the degree? This is 1, right? So we have one pole at origin, so that's why we would have said this is type 1 system, right? Very simple. Okay, but you know, our system is this. Okay, so that's why we are calling this as type 0 system. Okay, so any doubt in this question? Very simple. Just find out the open loop poles at origin on. Okay, so next, this is last question. Okay, the characteristic polynomial of closed loop system is given where k is real parameter, then the closed loop system is stable for, okay, so s square plus k s square plus 2s plus 1 equal to 0. Characteristic polynomial is given. So you know what is characteristic polynomial, right? This is ds, right? So I'll write just closed loop transfer function is equal to ns by ds. Okay, and this ds is, we also call it characteristic equation, okay, or C short form, characteristic equation. Okay, so it is given in the quotient. Then the closed loop system is stable. So how to find out the closed loop system is stable? So you check for the sufficient condition. Okay, all the coefficients are non-zero, so we don't know about k. Okay, but so if we use the necessary condition, k should be greater than 0. Okay, because every other coefficient is positive, okay, and non-zero. So every SQ, S square, S1 and S0, all the coefficients are present. Okay, also if you make the Routh, construct the Routh array, what you'll get, so this is necessary condition, right? Right, necessary condition, at least k should be greater than 0. So SQ square and SC, okay, 1 k, this is 2, this is 1. Okay, you know this is 2k minus 1 by k. Okay, and if you find what is the coefficient, you will get 1 right here. Directly I'm writing. So just see this first column. Okay, so this column should not be 0, and also you have to ensure there shouldn't be any sign change. Okay, so how to ensure that if k is greater than 0, then this term will be non-zero, right? So this term will be positive, and what we have to ensure, this is also positive. Okay, it should not be 0, it should be greater than 0. Also this k should be greater than 0. Okay, just see, then if k is greater than 0, then this should be greater than 0 and k should be greater than 1.2. Okay, so if you see intersection of these two conditions, what you'll get is k should be greater than 1/2. Okay, so this is the condition. If you ensure this condition, then a closed loop system will be stable. Okay, so what we have, so we have got this condition, k should be greater than 1/2. Okay, so nearest is this first option. Okay, if we ensure that k is greater than 1, then our closed loop system will be stable. Okay, so any doubt in this question? Very simple. Okay,
So you could have chosen the third option, right?
third option, k, no, we have to choose k whose value is greater than 1/2. Okay, so if we choose the third option, not you'll get, okay, you'll get this coefficient. Okay, you'll get this coefficient to be positive, right? But what about this coefficient? Okay,
So
let's choose k to be 0.1. 2 into 0.1 minus 1 by 0.1. Okay, what you'll get? This is 0.2 minus 1 by 0.1. So this is negative, right? This is what? 0.2, this is 0.8. Getting the point. So this will become negative. Okay, if I choose k greater than 0. So I'm choosing the intersection, like,
yes, understood. But you could have chosen
yeah,
2 also, right? That is greater than 1/2.
yeah, like closest I'm choosing. So actual answer is, if k is greater than 1.2, okay, yeah, that is also correct. If k is greater than 2 also, we are satisfying the condition, but closest is k is greater than 1, right?
Okay, sir.
If you keep any value k greater than 1, you'll satisfy this closed loop. No problem. Okay.
Understood.
Okay. So any doubt for today's session, like any question you have doubt from 1 to 15? Okay, so let me just scroll up. So you can ask any doubt
Thank
you
you.
have. Yes, sir. Okay. So 10th. Two and one. Okay. So any doubt? Okay, I think okay. In case we don't have any doubt, we'll close the session for today. So thank you for attending this session. So I'll meet you in the next session on Tuesday on 6 o'clock. Okay. So thank you for attending this session. Good night.
Okay, thank you.
Thank you.
Thank you, sir.